Hello, my radar system engineer. Today I'm going to present to you my radar lecture series, serial number 001. And the subject of the title is called Radar Range Equations with S. My name is Piley Chen, also known as Peter Chen, from Radar Consulting, California. Here's my brief technical summary. I've been working radar for over 40 years. Mainly in the airborne surveillance radar, missile seeker radar, multifunction AESA radar, and also aircraft landing radar. I have been held many technical positions as the technical director for NATO radar system, chief scientist, chief radar engineer, and also lead radar system engineer. Also, I've worked several missile seeker IR&D as the principal investigator, and also I serve as manager of radar system engineer while I was with Hughes Aircraft radar system and Raytheon space and airborne system. And these are the companies I used to work for, such as the Raytheon space and airborne system, Hughes Radar System Group, Boeing Defense, Texas Instruments, RCA, Lockheed Martin, Surface Radar System, mainly the naval system, and Rockwell International Aeronautics, working in the PAC-3 missile seeker, and also TRW and Telephonics Radar Corporation. These are the three books I've been published. The first one is called Integrated Airborne Surveillance Radar. The second one is called Millimeter Wave Aircraft Landing Radar. And the third one is called Space-Time Adaptive Processing with MATLAB simulation. I acquired 3 U.S. radar patents while I was working for Raytheon and also Rockwell International. I published several radar papers in the radar conference and also international radar symposium. And also I have several radar proprietary disclosure. As far as radar range equation, today we're going to talk about the pulse radar. And also it's based on a monostatic radar system, meaning transmit and receive on the same radar platform. So for such a pulse radar system, we're going to talk about 3 types of different radar range equation. One is called a single pulse radar range equation, and the second one is called integrated radar range equation. And third one, perhaps is the most useful radar range equation, is the radar search range equation. And finally, I will propose present a design example to show how the things all link together. All right, let's start with the single pulse range equation. All right, here is the range equation SNR1. Notice 1 means no pulse integration, it's just a single pulse. Equal to the denominator is the PT, which is the peak power. Not average power, the peak power. And the tau is the raw transmit pulse width, not the compressed pulse width, it's the raw. And the GTGR, transmit and receive antenna gain, lambda square sigma t, which is the target RCS. In the denominator, there's the 4 pi cubical, range to the force power, KTS, and total system loss. Now, sometimes the TS is the system temperature incorporate the noise figure. In this case, you don't see noise figure because the TS actually incorporate the noise figure. Now, the above SNR1 equation, which is not normally used because it involves a lot of numerical a tedious calculation. Instead, if you take the logarithm with the 10 base, you get a bottom equation in terms of the dB. So SNR1 dB equal to PK dB watts plus 10 log tau second, GTdB, GRdB, plus 20 log lambda in meter. In the denominator, you will see all in minus, because once you take dB, it becomes minus, right? And the 40 because r to the 4th, and 10 to the k is the Boltzmann constant, and subtract by 10 log Ts and the loss in dB. So the second equation in dB is most often used in the radar range equation analysis. Now here are the set of radar system parameters which we're going to illustrate to plug in the second equation in dB using the Excel spreadsheet. The peak transmit power is set up for 300 kilowatts. Notice it's a peak, and the transmit pulse width is 3 microseconds and compressed. And these are the antenna again, both set for 34 dB, and with our wavelength is set for 10 gigahertz. Target RCS is 1 meter square, and the 4 pi cubical is 1981.38, and the detector range nominally we set up to 30 kilometer, and these are the Boltzmann constant, system temperature, that's including the noise figure, and also total system loss of 4.5 dB. All right, here is the Excel spreadsheet using the dB equation. So you see the peak transmit power 300 kilowatts, and you take 10 log of that, become 54.8 dB, and etc. for all the system parameter in the numerator, and you put under the column called positive dB. All right. Now in the denominator, you put in the negative number. These are the negative numbers such as minus 33 dB based on the 4 pi cubical, and the detection range for 30 kilometer turned out to be 179.1 dB kilometer, and etc. etc. So you go through the calculation, you add the positive dB with the negative dB, you end up with the SNR1, which is 22.4 dB. Now this is a pretty high dB requirement for SNR1. So what is the useful things about SNR1? All right, not a whole lot, but it is a good start up for all the initial radar system parameters set up. So it really for later design trade-off, and you notice that it requires a very high power times antenna aperture product to achieve the Rmax, the maximum detection range. And most importantly, if you use single pulse, there's no radar waveform design involved, which cannot increase the SNR and also cannot resolve the range ambiguities such as the range and velocity. And you don't take advantage of a frequency agility, which you can improve the target detection to avoid the target fading, plus others. So what's next? The next step is employ pulse integration to basically reduce the SNR1 requirement. And most importantly is the number 2 bullet. You have to associate the SNR after integrated many pulses associated with the PD, probability of detection, and probability of false alarm, using the equation called the Albertson equation, which I'm going to show you later pretty soon. And to further improve the detection performance analysis, you might want to incorporate the target swirling models and waveform design to finalize the design trade-off. So with all the parameters listed, and you do the initial analysis, and you can start to do the trade-off among all the system parameters, such as the power aperture product, the beam dwell time, angle coverage for the antenna, and also the overall system timeline. All right, so let's talk about pulse integration. Now, the incorrect way to do pulse integration is simply times the NP. All right. This is only true when the condition for integration is perfect, which is not realistic in a realistic radar environment. More importantly, there's no association with the probability detection and also force law. So the correct way is to use so-called Albertian equation to link SNR, number pulses, PDPFA. Now, this is also known as the Blake's analysis. Blake is the radar system engineer who linked SNR, integrated SNR with the PD and PFA and number of pulses. So, Blake analysis in general to be considered one of the most complete radar analysis. Now, what is the Albertian equation? The Albertian equation is lists as SNR required for maximum detection range. It's a function of number of pulses you integrate, N, and also PD, all right, and the PFA. And PD-PFA is associated with the parameter A and B. And notice these are natural law, right? And also after you do impulse integration, you will find out the integration gain is also a function which is designated by I and P. It's a function of PD-PFA and number of pulses. And the integration gain, which is sometimes people call detectability, or Blake's detectability factor, sometimes denoted as a D1 NP. So the SNR required after integration for maximum detection range is equal to the single pulse subtract the integration gain. All right. Now this Albertian equation is very accurate as long as you integrate the number of pulses less than 96, which is a very high number. And also the probability detection is from -3, false alarm -10 to the -3 to 10 to the -7, and PD is from 0.1%, 10% up to 90%. Now the question is what is our Albertian equation, how this equation is derived. So if you recall back in the 1960s, there's a radar book, it's called Radar Detection, and it's written by DeFranco and Rubin. In that book, there are many detection curves, which is basically detection range, SNR, versus very multiple curves of PD-PFA. And the Albertian is the person who did the polynomial fit, and that's how he come out the SNR required. And this is a very nice equation. All you have to do is plug in PD-PFA, you will find out what is the SNR required to achieve the maximum detection range. There is a numerical illustration how you actually calculate the A and B. So you go through the thing, make sure you know how to calculate this number without making a mistake. For example, you plug in your PD 90% to calculate the B parameter, and you calculate the PFA relate to A. You get the A equal 13.341, B equal 2.197, and you use N equal 10 pulses. You go to the Albertian equation, you find out SNR equal to, go to this equation, you find out the SNR actually is equal to 4.997, right? Which is a much lower than the single pulse value because of the integration gain. All right, and also let's go to the calculation again. What is the integration gain? So you plug in all the number to find out the I and P. That's the integration gain. All right, with the PD, PFA, and you find out finally the integration gain is equal to 9.09 dB. Now, If you take 10 pulses, the conventional non-accurate way is 10 to the log 10 equal 10 dB. If you go through all this calculation, you get a 9.09 gain. So there's an integration loss because Albertson equation is dealing with a non-coherent integration. This number, the difference between log 10 log n versus the Albertson equation INP gain is very small, only 0.81 dB. But if you increase the n, increase the PD, the integration gain will be actually the integration loss will become larger. Now here's you plug in the Albertson equation into a MATLAB simulation. This MATLAB simulation is for n equal 10 pulses and PD equal 90%, PFA equal 10 to the minus 6. So for the first n equal 1 case, which show up in blue curve, you get SNR required is 9.2 dB. But if you go to n pulse integration, you will get into integration gain of 8.6 dB. That means you only need 0.6 dB to achieve the PD PFA. So this is the nice thing about integrate n pulses, all right, also associated with the PD PFA. So this plot is mainly based on Albertson equation. Input n, input PD PFA, and you get SNR required as a function of PD. You put many different other pulses, such as 10, 20, 30, and 40. And you're going to find out a different curve, all right? And for example, if you integrate more pulses, your integration gain will get more. So this is a very useful design curve to do the design trade-off. How many pulses you're going to integrate it, all right? What is the SNR required given the PD PFA? So this presents a very nice design trade-off, the foundation for later on define a radar system analysis. Okay, let's list what is the integrate radar range equation.
Integration is used to add large values in mathematics when the calculations cannot be performed on general operations.
All right, this is the integrate SNR, which employ pulse integration and design as the R max to the fourth power equal to the numerator and also the denominator. Notice the denominator is the SNR required. It's not the SNR1, right? So the SNR required is equal to SNR1 subtract integration gain, right? And this is the SNR equation to achieve the maximum gain using the integrate SNR. Here's a summary of integration gain and loss, which we talked about already. The SNR required equal to SNR1 minus the integration gain. And the integration gain, in this case, is written as INP in terms of dB. It's a function of the PD, number of pulses, and the PFA. And also the integration gain, sometimes you're going to see, the integration loss as a loss, NCI in terms of dB, which is equal to 10 log NP subtract the integration gain. All right. Now, here we change the name of this integration, maximum integration performance into a thing called Blake analysis, which is basically taking a log of the range equation and in terms of dB, right? And you can see the 40 log 10R equal PT, which is the peak power, etc., etc. But notice, the most important thing is the SNR requires plug into the range equation. So on the bottom, there are two range equations. It's just different form of the range equation, but basically the top dB equation is the most often used in the radar range equation analysis. All right, here's a set of a system parameter we are going to plug in to illustrate how SNR integrated and how to calculate all the values. So these values we put in, some are for information, some are plug-in for calculation. For example, remember SNR1 without integration is 9.1 dB, and the integration gain is 8.5 dB. So the required SNR is really 0.6 dB. So you plug in all the system parameter and plug into the radar range equation, and you will find out the maximum range achieved with only 0.6 dB after you integrate number of pulses and given the PDPFA, which is very reasonable to calculate, right? And the Excel spreadsheet is going to illustrate how these numbers is going to be plugged in. Right, here's the Excel spreadsheet to show you how you actually plug in the system parameter. All right, so on the left top corner, you see the SNR1, DMP, and also the SNR required, just for the information. And on the bottom rows, starting with the peak power, you plug in, 300 kilowatts, all right? And you got 54.8 dB. You plug in transmit pulse width, I believe it's 3 microseconds, etc. All the system parameter on the numerator is shaded in green, which designate the positive dB. All the system parameter in the denominator show us in kind of an orange color. That means in negative number. So when you add the positive dB with the negative dB, you will find out the R max you can achieve with only 0.6 dB is 189.9 dB kilometer. All right, and which translates into that's R fourth. So R max, right, is 4.7 dB kilometer, and you convert to R max in terms of a kilometer, which is the 55.9 kilometer. So this is a very important Excel spreadsheet you must get yourself familiar with. And I know it is difficult to read from my presentation. Actually, I have the actual Excel spreadsheet. You can contact me. I will email to you. You can play with this number and make sure you plug in the right unit, and make sure you plug into the positive dB column and negative dB column to make sure you will get the same number as I do. So with that, you are familiar with this kind of a calculation, which is very important as a radar system engineer to show yourself how to do radar system analysis to calculate the Rmax using the integrate SNR to do accurately the maximum detected range. Also, you got to tie up the SNR with the PDPFA. This is very important. Now the question is how many pulses are available for integration? Now this is the question which we're not talking about it because it's related to the antenna beam dwell time times the radar PRF, which is another subject by itself. In the later example, we will show you how you actually find out the dwell time, how to utilize the best PRF, etc. And very important is the time, is the frame rate of the update rate, and make sure all the system parameter, you put a dwell time, you put the number of pulses integrated, you do the search for the big capital omega, which is the angular volume. Everything is consistent with the system timeline. Now, after you do all that, if you find out your signal to noise ratio detection probability is still not sufficient enough, there is a way, other ways to improve the PDPFA performance, which we're not going to talk about here. These techniques such as the M out of N detection or cumulative detection. So these are the other subjects to further improve detection performance. All right, now we're getting to a search radar range equation. This is the most important subject in this presentation. Is because this has a real application in the real world radar design. Okay, this chart shows the antenna try to search a big omega volume, angular volume, and try to find out where's the target is. Now, right now, we're only showing one single target. In the reality case, realistic case, you're going to see multiple targets, all right? And the antenna scan can be used either mechanical or AESA, which we're not going to address this issue yet. But notice we need to pay attention to the dwell time. The dwell time has nothing to do how you do antenna scan, whether it's mechanical or whether it's AESA. It is the time you must spend for the antenna to dwell at a certain beam position. Here's a summary of integration gain and loss, which we talked about already. The SNR required equal to SNR1 minus the integration gain. And the integration gain, in this case, is written as INP in terms of dB. It's a function of the PD, number of pulses, and the PFA. And also the integration gain, sometimes you're going to see, the integration loss as a loss, NCI in terms of dB, which is equal to 10 log NP subtract the integration gain. Right, here's just a summary of all the system parameters, which I'm not going to dwell too long to talk about these parameters. All right, and this is the power aperture product versus different antenna diameter as a function of average transmit power. Basically, power average power on the y-axis, antenna diameter on the x-axis for 3 or 4 different kind of a range of detection. So you can find out for a certain range, maximum range detection, all right, you will find out what's the power aperture product. All right, Now we're getting to search radar range equation. This is the most important subject in this presentation. Is because this has a real application in the real world radar design. All right, again, we list the radar range equation again. And notice this time we have a requirement, which is on the left. The requirement is something you cannot change because that's the customer requirement, which include search volume, frame time, maximum detection range, and the target RCS. Then on the right-hand side, you have a performance parameter, such as the SNR, PD, PFA. Then the performance parameters linked to radar design parameter. These are all radar subsystem parameters, such as transmit power, antenna gain, wavelengths, number of pulses you can integrate it, the dwell time, system temperature, and system loss. So what you do in this environment, you take in a requirement, you understand the performance you have to meet, and you go to the radar design parameter, which is designated by this green arrow, which is two-way arrow. You can go both ways to find the balance. And finally, you check the radar requirement. Now notice the radar requirement is one-way arrow. You cannot change the radar requirement. But what you do is you base on the performance, you do the radar design parameter trade-off. So you go through many different iterations until you find out what's the reality meet the radar realistic design. So this is an iteration process for you to go through to make sure you understand how the radar search range equations actually apply. Now notice all these radar system parameters, each one representing a radar substance specification. So by doing that, not only you do radar system performance, try to meet the system requirement, you also kind of establish the initial radar subsystem specification. So make a long story short, understand radar system design using the SNR required is a very important technique for you to mature to be a very senior radar system analyst. Here's the illustration, only show plus 45 minus 45 a field view how many beams position you need to deploy. And in this illustration, we want to design the maximum detection range is 20 nautical mile, and only for illustration, we show plus minus 45 degree. The actual calculation, we're gonna do a 360 degree coverage. And the azimuth beam width, we are assuming using 1 degree azimuth beam width. So let's just relist the parameter we're going to use. The total angle coverage is army direction, 360 degree. Let's set up the frame time to 2 seconds. Let's set up the azimuth beam width 1 degree. So you have total 360 divided by 1 degree. So you have 360 degree beam positions. Now assuming the elevation beam width is enough to cover. Now in reality, you have to find out whether elevation beam width is enough. Otherwise, you got to do elevation scan, which will kind of complicate the process. All right, but right now, let's just for simplification, we only do azimuth scan for 360 degree, and frame times 2 seconds, and the beam width in azimuth is 1 degree. All right. So what we try to find out is how many beams actually want to dwell, all right? And how many beam we're going to deploy, and what is the antenna beam dwell time, all right? That's the thing we try to find out. Now, in order to do that, you have to find out the PRF, all right? Let's assume the 20 nautical miles is the maximum detection range. And let's assume the detection is ambiguous. So for 20 nautical mile, a good choice of the PRF is 4.076 kilohertz. So you take the PRF, 4.076 kilohertz, times the antenna dwell time, 5.56 milliseconds. You will get the total pulse for integration is 22.6, and rounded off, it becomes 23 pulses available for pulse integration to reduce the SNR1 required. Now, as far as antenna parameter, you really have to do antenna design trade-off to find out whether this antenna give you enough power aperture product to give you enough SNR. Right? Here, just list on the right side corner for a reference. How you get this number is another trade-off. So in this chart, we got to remember the coverage 360 degree, the frame time is 2 seconds, the number of beam positions is 360 beam positions, and the total, not total, the single beam dwell time is only 5.56 milliseconds. And the available number of pulses for integration is about 23 pulses, right? So with this number available, we put it in the Excel spreadsheet. This is only part of an Excel spreadsheet, all right? So you put this number in the Excel spreadsheet. What you're trying to find out is the single pulse for swirling target 1, you need a 17 dB. All right, for 23 pulses, actually we show 22 pulses, you can get 12.2 dB integration gain. So the actual SNR required is only 4.8 dB. All right. Now here's the Blake calculation. Basically, it's the same Excel spreadsheet which I showed you before. Notice you plug in the SNR required is only 4.8 dB. All right. The rest of the number you just plug in as the previous shown before, and you will find out what is the maximum detection range. Turn out to be 36.8 kilometers. In terms of nautical mile divided by 1.85, you get 20 nautical miles. All right. So here's a summary about the lecture 1 radar range equation. The most important things is we want to use integrate SNR, which is designated as SNR required. It's a function of PD and PFA, right? And we want to use the search range equation, which is the most useful range equation in the radar range equation. And also you will find out other applications such as the Iron Dome, Space Dome, air defense radar system, etc., etc. All right. Now each one can be a separate design example, but they all use this Blake analysis. They all use this integrate search range equation. This is why this lecture is really emphasize how important this radar search range equation, how useful it is. And you have to familiar with yourself with this technique. Otherwise, you cannot be a very senior or expert radar system engineer. All right. So basically, this is the lecture number 1. All right. So here just kind of a summary about the range equation. SNR required is a function of number of pulses, the PD, PFA, and how to calculate integration gain, and actually to find out the SNR required. So notice the SNR required has to tie up with the PD and PFA. Now, I know there's a lot of equation, Excel spreadsheet is hard to read, but you can contact me for a copy of the Word document of this presentation, which explains much in depth. I also have all the MATLAB simulation to plot all the detection curve, along with all the Excel program to do Blake analysis, etc. So if you need it, please contact me. A small fee may be acquired because it takes time to put the things together. Again, this is Pilot Chen. You can contact me at pch1948@yahoo.com or radarconsultingcalifornia.com.